When we think about soil, it's so easy to just dismiss it as, well, dirt, something to hold plants up. But that view is just plain wrong. The ground beneath our feet is actually this bustling, incredibly complex, living system. It's a dynamic marketplace that makes all plant life possible, and today we're going to figure out exactly how it all works. Yeah, look at this. It all starts right here. You see these beautiful green shoots, and you see life, right? But the real story, the secret sauce to all this growth, is happening down below, in that dark, rich soil. This healthy plant is the direct result of a thriving, invisible world that's constantly working. So that begs the question, doesn't it? What is actually going on down there? How in the world does a bunch of soil manage to feed a plant? And what makes one patch of ground fertile and another totally barren? All right, so here's our game plan. We're going to start by taking a peek inside the soil's nutrient pantry to see where the food is stored. Then we'll head over to the soil solution marketplace, which is where all the action happens. We'll find out how plants actually shop for their food, and we'll meet the nutrient gatekeepers who control the supply. And to wrap it all up, we'll follow the very different journeys of two superstar nutrients, nitrogen and phosphorus. First stop, the nutrient pantry. See, to get our heads around how plants eat, we first have to figure out where the food is even kept. These nutrients aren't just, floating around randomly. They are stored in very specific places. So, there are three main storage units in this pantry. First, you've got the soil minerals themselves, the tiny bits of weathered rock that form the backbone of the soil. Second is organic matter, which is all the decomposed stuff from plants and animals. We call it humus. Think of it as a slow-release nutrient capsule. And third, and this one is absolutely crucial, are the cation exchange sites. And that brings us to a really, really critical idea: cation exchange capacity, or CEC for short. The simplest way to think about it is that CEC is a measure of the soil's pantry space. See, tiny soil particles have a natural negative charge, and a lot of the nutrients plants need, like calcium and potassium, have a positive charge. The CEC tells us just how many of these positive nutrients the soil can hang on to, preventing them from just washing away. Okay, take a look at this diagram. It shows you exactly how this works. See those big particles? Those are our negatively charged clay or humus particles, and they act like little magnets, attracting and holding on to all those little positively charged nutrients. They're not locked away forever, but they're held in reserve, kind of like being on the pantry shelf, ready for the plant when it needs them. So here's the bottom line. Just think of CEC as the soil's nutrient magnet. A soil with a high CEC, say one that's rich in clay and organic matter, has a much stronger magnetic pull. It can hold a bigger bank of nutrients, making it naturally more fertile. Simple as that. All right, so the nutrients are all stocked up in the pantry, but obviously they can't just sit there on the shelf. To be useful to the plant, they have to get to the checkout counter. And this happens in what we're calling the nutrient marketplace. Now, this marketplace is something called the soil solution. And really, it's just the water that's held in all the little gaps between soil particles. And here's the key. Nutrients must be dissolved in this water as ions for a plant to have any chance of grabbing them. If a nutrient isn't in the soil solution, then as far as the plant is concerned, it might as well not even be there. And this quote from our source material just hits the nail on the head. The soil solution is the essential transport medium. It's the highway that brings those nutrients right up to the front door of the plant root. No solution, no delivery. Okay, so the nutrients are now in the marketplace, dissolved and ready to go. How do the plants actually shop for them? Well, it turns out they have three main strategies to get the groceries they need. First, there's simple root interception. Think of this as just dumb luck. The root just happens to be growing along and physically bumps right into a nutrient. But the two real heavy hitters are mass flow, which is kind of like a nutrient delivery service, and diffusion, which is a much slower process driven by good old supply and demand. So let's compare these two. Think of mass flow like a river. As the plant sucks up water, it creates a current, and this current just sweeps all the dissolved nutrients along for the ride, right to the root. Diffusion, on the other hand, is all about balance. When a root absorbs a nutrient, it creates a little empty spot right next to it. So other nutrients nearby naturally move from the crowded areas into that empty spot to even things out. And this is fascinating. Look at this table for corn. It shows that different nutrients use totally different shopping strategies. Nitrogen, it gets almost all its supply from mass flow. It's riding that water taxi straight to the root. But then look at phosphorus and potassium. They almost exclusively rely on that super slow, short-distance process of diffusion. This difference is a massive clue about how these nutrients really behave in the soil. So that brings us right to the gatekeepers, the processes that control whether a nutrient is even available to be picked up in the first place. Why is nitrogen getting a free ride with mass flow while phosphorus has to wait for diffusion? Well, it all comes down to one word: mobility. Now, the first set of gatekeepers are the trillions of microbes in the soil, and they are constantly in this epic tug of war. Mineralization is when microbes break down organic matter and release nutrients into a form plants can actually use. But immobilization is the exact opposite. The microbes themselves eat those available nutrients for their own growth, temporarily locking them down. So, what decides who wins this tug of war? It's all about what you feed the microbes, specifically something called the carbon to nitrogen ratio. Microbes need carbon for energy and nitrogen to build their bodies. If you give them something super high in carbon, like straw or wood chips, with a CN ratio over 30:1, they've got tons of energy, but they're starving for nitrogen. So what do? They suck up all the available nitrogen from the soil for themselves, putting it on lockdown and leaving none for the plants. The other major gatekeeper is just basic chemistry, the nutrient's own electrical charge. Remember how our soil particles are negatively charged? Well, like charges repel. So negatively charged ions like nitrate get repelled. They don't stick to the soil, so they stay mobile in the water. Perfect for mass flow. But all those positively charged guys like ammonium and potassium, they get held tightly by the soil's magnetic CEC, which makes them immobile. And phosphate is a whole other story. It binds so tightly with soil minerals that it's also extremely immobile. Okay, let's bring all of this together. We're going to look at two case studies to see how all these concepts play out in the real world: the fast and loose journey of nitrogen and the slow, steady path of phosphorus. Nitrogen's journey is a sprint. It starts locked up in organic matter. Microbes mineralize it to ammonium, and then other microbes quickly turn it into nitrate. And as that mobile, negatively charged nitrate, it gets swept up super easily by plant roots. But here's the catch. That same mobility that makes it easy for plants to get also makes it really easy for rain to wash it or leach it right out of the soil. Easy come, easy go. And then there's phosphorus. Its story is the complete opposite. It's held incredibly tightly in the soil's pantry. Only teeny tiny amounts get released into the soil solution at any one time. And once it's there, it moves at a snail's pace, and only over very short distances, waiting entirely on diffusion to hopefully get nearer roots. And this is the practical result of that immobility. Since phosphorus won't come to the plant has to go to the phosphorus. This is why plants have to develop these huge, sprawling root systems and even partner up with beneficial fungi. They're trying to explore every last inch of soil to find these critical but hard-to-get nutrients. So when you look at the ground, it's not just a foundation, is it? It's this complex, living marketplace with its own rules for storage and exchange and transportation. Understanding how it all works shows you just how critical it is to protect our soil's health. So the question to leave you with is, now that you know how this marketplace works, what will you do to protect it?